and I'll hand over to you, Luke. So welcome everyone. It's great to have you all join us for this Zoom talk for the Irish Meteorological Society, the Irish MetSoc. We should have more Zoom talks, so we're going to try and start fitting more of these in to help people who can't make it in person to the Custom House. And likewise, if anybody's joining us today who hasn't been to our in-person talks in the Custom House, please feel free to pop by anytime we're having a talk. You can always see what our talks are on our website, the Irish MetSoc, and feel free to drop by, see a talk, come in, chat to us. And if you're interested, of course, you could always join the society, which helps us run everything well. So this month, we're really pleased to have Luke Barrington from Google come to give us a talk on what is really the topic in weather and climate modeling at the moment, which is the revolution of AI. This is, of course, a really good timing for us in the society as well, because we just had last month that great talk from Thomas, who in Med Éireann, who has been looking at AI and gave us, I think, a really good overview of the different activities going on in AI and forecasting at the moment. So it's great to get this focus from Google's point of view that Luke Barrington will be able to give us today. So Luke has sent me a brief bio here. So he's product director in Google Research, where he works on AI for Earth. Luke works across Google's geospatial research teams, helping transform AI innovations into products that impact the planet. His work today includes machine learning models for forecasting weather and natural disasters, mitigating climate change, and creating a complete current 3D map of the Earth. That sounds pretty exciting. So we might just kick off straight away then. If everyone is on mute, it looks like you all are. That's great. I'll ask Luke to start his talk. Thanks, Luke.
Cool. Thanks very much. It's a pleasure to be here today, or to be virtually with you today. As Conor said, my name is Luke. I'm based here in Dublin, grew up in Ireland, went to UCD, did my PhD in California, and then I've worked for Google in both the States as well as here in Ireland. And yeah, I'm here today to talk to you about our work in weather forecasting. And just to give a bit of motivation, when I'm giving a talk like this, I normally start off with this stat, which I love, which is that 94% of us here in Ireland talked about the weather in the past 6 hours. I'm assuming with this audience, it's up to 100%. But talking about the weather is one of our national pastimes here. But it's more than just a sort of a funny anecdote. Here at Google, we know that weather touches all aspects of people's lives. And it's actually, this manifests as being one of the top 10 Google search queries worldwide. And this little graph on the right shows you, people, it kind of spikes in the morning when people are Googling the weather, checking the weather to see how their day is going to be like, what they should wear, if their kids' school soccer practice is going to be cancelled, or if they should go for their run in the morning or the evening, and then they check again kind of at nighttime when they're kind of planning for the next day. So this, touches really a huge part of our kind of day-to-day lives, and that's manifest in many of the products that Google builds from. But of course, it goes, much deeper than that. And one of my kind of, I think the most compelling ways to put this is that really climate, which we're all concerned about, and hopefully this chart will hit it home if any of the other 10,000 things you heard about this year haven't already. The planet is warming. We're the reason why. But the way that we're actually, I think one of the challenges with climate change has been, oh, well, that's a problem for the next generation, or what can I do today, or what difference does it make to me? Well, the difference it makes is that weather is just climate in the short term, or said another way, climate is weather over the long term. And so the way that we're experiencing climate change here on Earth today, right now, is through changes in the weather. And so as we get into this, better understanding of the weather is actually one of the best things that we can do to help us deal with and perhaps even mitigate the changing climate. I'll talk more about that at the end. So I just want to start a little bit with, how this is all great to say that, it was a big deal, whether from day-to-day use cases to the long-term climate change, but how do we actually solve this amazing puzzle of, figuring out what's the weather going to be tomorrow and in the future? And I'll just kind of talk a little bit about, it's pretty simple, really. You just have to solve this, right? Figure out all of the different dynamics of how the atmosphere is moving and energy is traveling through it, how changes in solar inputs, atmospheric chemistry, all the way down to the ocean coupling and the land surface models. And of course, all the stuff that we as humans are doing to that land surface is, the solution to solving this planet scale problem. So it's actually one of the, I think, the grandest challenges that's faced humanity. In fact, this has obviously been something that humans have puzzled about for millennia, from the old kind of anecdotes of red sky at night, shepherd's delight, and these kinds of things. Trying to figure out how weather is going to affect the food that we grow and the lives that we live has been a huge part of kind of human innovation. But that kind of really got serious about in the last century. And I'm going to talk a little bit about how numerical forecasts work today. Again, I'm assuming at the Irish Meteorological Society that you're all experts in this. This is just going to set the basis for what we talk about in the kind of main bulk of the talk around AI. But at a very high level, you start by chopping the world up, the Earth up into a three-dimensional grid. So not just the surface of the Earth, but also up into the atmosphere, of course, which is a huge influence on modeling the atmosphere. And then we're going to try to solve the problem in each of these grid cells individually. And the solution to that problem is from running this dynamical core, basically solving the equations of physics that govern the motion of energy and heat and moisture and all that kind of stuff through the fluid dynamics of these on this rotating sphere. So within each cube, solving these equations. And I'm not going to solve these equations right now. I have no clue how to solve them. Some of them are known. I just wanted to give one shout out. The core of this is the Navier-Stokes equation, which many of you may know. The Stokes in the name of that equation set is George Stokes, born in Sligo. And so it's nice to see that Ireland has had a kind of a pioneering role in weather innovation for more than a century. But solving those equations is one thing, but actually, how do you kind of resolve all of the little bits that go on inside those boxes? So like our current best weather models right now, each of those cubes that we're illustrating might be kind of 10 kilometers on a side. And so, in other words, there's many, many things going on inside a cube that we're not really modeling, that we're not really seeing. So that's just the formation of clouds, clouds turning into precipitation. All of these things happen at a much smaller time scale or spatial scale. And so for those, we use a bunch of physical approximations. Basically, thousands of PhD theses have gone into figuring out, how does clouds precipitate over the Sahara, and how does them different, local phenomena affect each of these cubes, and we kind of parameterize those inside the model. So you got this solving kind of the raw physics equations with a bunch of approximations and kind of parameterizations in the physics suite, and then you take all of that and you bundle it up into a massive big computer program, which you run on some of the world's largest computers. So in many cases, these are supercomputers based in government labs and in the basements of research centers that grind on all of this data, all of these observations, solve these physics equations, make these approximations, and try to simulate the next step in the weather forecast. So that's basically how weather forecasting has worked for the last 50 years. In fact, even before computers, people were doing this by hand. But over the last 40 or 50 years, there's been quite remarkable progress in the performance of these forecasting models. And so what this graph is showing on the time on the x-axis and forecast model accuracy. So in the blue chart is like a 3-day forecast. The red one is a 5-day forecast. Green is a 7-day forecast. And in a nutshell, what you can see is that today we enjoy a 7-day forecast that is about as accurate as was a 3-day forecast, back in the early 80s. So really, quite 4 days of improvement. If you're planning a picnic a week from now, you might have the same kind of confidence in whether it's going to rain or not as you would have had, 3 days in advance, in our parents' or in our grandparents' time. And so what has caused these improvements? I want to kind of highlight two real, I think, innovations. The first one was around at the turn of the millennium, and we started launching and operating global observation satellites. So now, rather than just relying on the data that we could collect at our local weather station or from the balloon that we might launch up from that weather station, we could get a kind of a bigger picture of the Earth as seen from above. And this gave us information about what was going on over the oceans and at the polar caps and all that kind of stuff, which is obviously going to be instrumental in determining what the weather might be on land, hours or days hence. And then the second big bump that we got was by putting weather stations on airplanes. And so now we could get not just kind of a one view from on high, but a kind of a slice through the upper atmosphere of what was going on in the atmosphere, and use that to kind of predict the weather in the atmosphere over the Atlantic today is going to be what the weather in Ireland will be tomorrow or the day after. So these two sources of new observations were kind of key in both narrowing those error bars. By the way, the gap between the high and the low of each of the colors is for the northern versus the southern hemisphere. And so you can see that the southern hemisphere, the global south, has typically had worse weather forecasting performance because we had fewer observations and less effort spent on modeling. But by having these global sensors, we were able to narrow that gap and also kind of have a few little jumps up in this accuracy of the modeling. But ever since then, kind of the early 2000s, the progress has really just been a slow, steady march of improving the code in the modeling and running them on bigger, better computers. And we haven't really seen another one of those kind of discontinuous jumps in performance that we saw from those two new kind of observations. And so the question we've kind of been asking ourselves in the AI community and here at Google Research is, what could we do to see another jump in the curve? What's the next big innovation that we could bring to weather forecasting that might kind of improve it even further? And if you haven't been living under a rock for the last 2 or 3 years, you probably know the answer to this question already, or at least our proposed answer to that, which is AI and machine learning. So for the rest of the talk, I'm going to talk about a couple of different AI weather forecasting models that we've developed here at Google for different kind of weather time horizons. Some of the ways that they differ, some of the ways that they're the same, and some of the ways that we're putting them into action. The first is a model called MetNet, and this is one of the first weather forecasting models that we published a few years ago, and it has been kind of updated. We're actually we're coming up to MetNet 4 now. This is MetNet 3 is the most recent publication. And the idea behind MetNet fundamentally is that rather than dealing with all of that physics nonsense, let's just use a neural net to take the data that we observe about the atmosphere in and to make predictions about the forecast out. And so inside the internals of this model, there is not the equations of physics or the Navier-Stokes or any of that kind of stuff, but rather just the pattern matching capabilities of neural networks, which we've seen be so powerful in many other domains. Another way to visualize this is you think about some of the kind of AI models that we've seen on predicting videos. You have multiple time steps in a video sequence, and then the goal of the model is to predict the next frame of the video. Well, instead of a video, what if you had observations of rain? So in this case, the example that I'm showing this image here, this is a network of rain radars that are distributed all across Europe. So these are radars that are based on the ground, usually at airports. They're the same radars that scan the atmosphere for airplanes. But the radar beams also bounce off precipitation in the atmosphere. So raindrops and snow and hail, that kind of stuff. And so by having this global, or this, in this case, continent-wide network of rain radars, we can see every 10 or 15 minutes or so with pretty good precision where in the atmosphere there is rain. And then the goal of the model is to simply predict, the next step or the next steps in that time series. And so what you're seeing on the right is the output of that model. And it's basically trying to estimate the probability of rain given the sequence of observations that we've seen from those rain radars. And then you can, the output of the model tends to be a probability. So it's like not exactly saying rain or no rain, but it's giving you a probability of rain. And so then the kind of forecaster's goal is to draw some threshold on that probability and say, I want to be 90% certain or 10% certain, whatever my goal is to make a forecast of how many, of if or when it's going to rain. So if you've ever looked at a radar app, like the Met-Éireann app has a lovely visualization of the rain radars over Dublin and Shannon, and you can see what happened 60 minutes ago, 45 minutes ago, 30 minutes ago, 15 minutes ago. But now what we're able to do is actually show what it's looking like 15 minutes from now, 30 minutes from now, and so on into the future. And it works. Here's just one of the evaluations from our paper that shows that the AI forecast has a lower CRPS score. So lower is better in this case for this particular metric than the physics-based forecast that we compared it to. And obviously that advantage kind of diminishes as it goes further and further into time. But particularly in those short-term nowcasting horizons, so like really trying to tell you, is it going to rain on your doorstep in the next hour or two? The model really shines there. And this is an example of the model running across the continental US, where in the middle you can see the ground truth. So this is the actual rain radars that we got, later on in the future. But on the bottom are the outputs of our MetNet precipitation prediction model, compared to on the top to the ENS, one of the numerical forecasts from one of the Met agencies. And a couple of things to observe. I already showed you that it was more accurate, at least in those kind of short-term precipitation times. But two other things you might notice, it also is much more finer in resolution in both space and time. So whereas the numerical models, those kind of cubes of the surface of the Earth that they divide the planet into, might be 9 or 10 kilometers on the side, we're able to bring those cubes down to just 1 kilometer on the side. So kind of giving you neighborhood level precision rather than city level. And also it's more, and you can see from this illustration that the time steps are also finer. So we're able to kind of make minute by minute predictions about when and where it's going to rain, rather than maybe running every kind of 20 or 60 minutes. So that's all well and good. We published a paper, we made some nice charts, but one of the things I think is the coolest thing about MetNet is that we're actually using this in production today. So for those millions of users who are Googling the weather every day, we're taking in those ground-based radar data, the satellite image as well. Our model also takes advantage of the three-dimensional topology of the Earth that gives you some extra skill in forecasting. And we use those numerical forecasts where available. And we're able to stack them all up over hours and hours and produce forecasts that are actually being now displayed to Google users in search. So for users in the US, continent and Europe, as well as just recently Japan, where we have that great ground-based radar, we're able to make these super accurate, super local rainfall predictions and give them to our users. So this is an example of the user experience on the Google Weather experience in search. So when you Google the weather, this is something that you might get. You see our famous frog, and then you kind of get this, I'm not sure if you can see my mouse, but this kind of blue box in the middle that's showing that output from that machine learning model that's predicting where and when it's going to rain. We've also launched this on Google Maps. So if you're browsing around the map and thinking about whether you might go into town for a picnic or rather go to the pub, you can check this and see where the rain, if it's going to rain. And just recently, we also launched it not on the new Pixel weather app, which doesn't just include these kind of text and graphical based alerts, but actually for the first time has this precipitation nowcasting map built into the app. That's a cool feature that I'm actually really excited about. It took us a lot of work. One of the things about this is, and it's something I'd love to kind of get some meteorological input on, maybe in the discussion section later on. Like I said, the model just outputs a probability of precipitation. How do you actually turn that into something to tell a user yes or no? It is going to rain, it isn't going to rain. Or how do you show it in the map? What color should different probabilities be? And how do you use those to give users confidence and understanding of the kind of probabilistic nature of these models? So this is, there's a kind of a non-trivial step of going from the raw model output into something that someone can actually make a decision about their day on. Since I'm here, my team had one request that I had to bring to this audience, which is in that Pixel weather app, which is absolutely beautiful and has this lovely map, we've unfortunately had to carve out a region around Dublin where we do not show the precipitation map. I talked to our colleagues at Met Éireann, and the rain radar in Dublin has been located, or is located, unfortunately, close to someone who's installed some new Wi-Fi antenna or something, or there's some weird interference that is causing this particular radar to have a glitchy return, which was causing our maps to look wonky and weird. And so we had to kind of carve that part of the model out, unfortunately. So if anyone has tips on how we could fix that, I'd love to hear it. So we're able to make this lovely map for regions of the world where we have this high resolution rain radar. But as this chart is showing, most of the world is not blessed with such high precision weather measuring apparatus. Most of Africa doesn't have rain radars. A lot of South America doesn't have them, or if they do have them, they're hard to get access to. Like many of these radars are operated by the Air Force and that kind of stuff, and they're not kind of made available commercially. And so we've been asking ourselves, this is kind of the next research horizon, I think, for some of these models is, what can you do for the rest of the world where you don't have these high resolution radars? And how can we provide that same kind of weather information to people all over the planet? One of the ways to address this is there are satellites that attempt to do what those ground-based radars do. This is a visualization of the iMerge data, which comes from kind of a global constellation of weather radars in space. But as you can see, you get some of this data, but it's both spatially and temporally not as dense or rich as the ground-based radars. There's also geostationary satellites that capture, an image of the full kind of, they call this the full disk of the Earth every 10 or 15 minutes. The European Space Agency has actually just launched a new geostationary satellite that we're very excited to get access to that data. Now you're getting kind of a real-time picture of the clouds from above, which is necessary but not sufficient to predict the rain on the ground. But by incorporating these observation data into the kind of nowcasting model that we described, we're optimistic they'll be able to provide a global nowcast. But this is kind of one of our current research directions. So that's going to, we'd love to be able to provide the same experience for users in India and Africa that users in Europe and Africa and America enjoy today. Okay, so that's the first model, the nowcast. But when I think about weather forecasting, I think about it really in three sort of fundamental time horizons. What we've just talked about is called nowcasting, and it's using, rich real-time observations to make high accurate in both space and time predictions about a handful of weather variables, particularly precipitation. But the kind of the bread and butter of forecasting for the last kind of century, or certainly those 50 years of numerical modeling that we showed earlier on, has been in that medium range forecast. This is like the 10-day forecast that you see after the news. That's, I think, one where until a few years ago, people were skeptical that AI could have anything to offer there, because physics does really matter, and the kind of proverbial butterfly flapping its wings in Japan has a chaotic effect on the weather in Ireland a few days afterwards. And then going beyond that kind of medium range, you get into sort of subseasonal and climate modeling, where really I think AI or many models have had little to say other than your best guess here often is, well, it was hot last year, so it'll be hot this year. Obviously, we've seen those sort of climatological predictions start to break down in the as the climate is changing. But so how might AI help us with these other horizons too? And so if we look back at that chart that I showed earlier on, I think if you'd asked a meteorologist 5 years ago, they would have said that this is sort of the path that we're on, and that AI does not have anything to offer there. And I think, you know, I might have agreed with them when we started exploring it with this. It was quite difficult to get any of these models to work at longer time horizons. But just in the last year or two, we're really saying, like, starting kind of beginning of 2023, and, you know, not perhaps coincidentally coinciding with, I think, seeing the rise of AI in a whole other host of disciplines, you know, and application areas across the earth. We've started to see for the first time AI models actually meet and possibly exceed the state of the art in forecasting at medium range. And so a handful of models up here in the upper right, this 100, you know, sort of like percentage skill relative to one of the state of the art numerical models. And now some of these AI models are actually starting to do better than that. So I want to talk a little bit about some of those and how they work. But just first of all, you know, these are been some groundbreaking research publications, and, you know, featured in Science and Nature and that kind of stuff. But also quite hearteningly, they've been, you know, the meteorological offices are also starting to take notice and actually put these into practice. And I'm very glad to hear that you had a representative from Met Éireann talking about this last month. Just a few days ago, I saw the ECWF publish the latest blog post for their AI forecasting service, their AIFS, and they've been using some of the innovations in those publications on the left to improve the models that they're working on the right. So how do they work? Well, to be quite honest with you, the AI weather models work just like any other, like AI models for any other discipline. And the key to success always begins with data. And in weather, we're actually blessed with a preponderance of data. But for this particular, I would say, revolution, it began with a huge reanalysis archive called ERA5 that is published by the ECWF. So this is basically, they take their latest forecast model and they rerun it retrospectively on all of the weather observations that we had seen over the last couple of decades, and say, what would we have forecast back then had we known, you know, had we the intelligence that we have now? And what it basically produces is this lovely, clean input-output data set. What we thought the weather, what the state of the world was, and what our forecast said. And it's bundled up over 40 years. So it was basically manna for machine learning researchers, a nice clean data set with lots and lots and lots of signal inside of it. So this was the first key, I think, that really kind of underpinned a lot of those breakthroughs that I showed on the chart previously. Obviously, the second piece, though, was, you know, applying deep neural networks to this data set. And so just as we've seen kind of things like transformers and graph neural nets make innovations on modeling large data corpuses of text or of images or of videos or of audio, so too those models tended to work quite nicely for weather. Now, of course, we had to make a lot of adaptations and improvements to the models, in particular, trying to understand the three-dimensional or the four-dimensional topology of the Earth and its, you know, the movement of the atmosphere through time, and kind of have models that could be cognizant of that was one of the kind of next stages. And then the third stage that's kind of been, again, fundamental to most of the AI breakthroughs in the last couple of years has been around compute. In this case, not supercomputers in government basements, but rather TPU and GPU processing units in cloud data centers. But again, vast amounts of compute that can really grind on these kinds of deep learning architectures and the data sets that we throw at them. And so you kind of take all of these trends and you take them from all of the other places that AI has been making inroads and apply them into the weather data sets. And sure enough, we saw some good results. You know, I'm going to get to the accuracy in a second, but one of the first things to call out is the speed. So by doing this in a kind of modern machine learning framework with the kind of software methods that go along with that, all of the optimizations and hardware that we've made to be able to make that work across all these different domains, we're seeing the AI models run far more quickly and efficiently than what you might expect from a numerical model running on a supercomputer. So this is just one illustration of one of our models, Neural GCM, kind of how many days of forecast it can produce in about half an hour versus what you might get if you were running one of the larger kind of numerical climate models. And it's not just faster, it's also using orders of magnitude less compute. And so when you add it all up, this ends up being like 3 or 4 orders of magnitude more efficient than running in a kind of a supercomputer NWP framework. But it is also more accurate. This is kind of a tricky chart, but this is the kind of thing that meteorologists might look at when they're trying to assess forecast accuracy, because the question is, you know, well, accurate at what? You know, for maybe I care the most about, you know, temperature tomorrow, but you care the most about, you know, pressure at 30,000 feet for your airline operations next week. And somebody else cares about the wind in the Maldives where they're going kite surfing next week. And so all these different variables are, you know, some models might be better or worse at other than, but I think the main thing to take away is anything that's in blue shows where one of the AI models listed here on the left are outperforming the kind of state of the art of numerical models. And so this is actually, there were so many of these different AI weather models appearing, and so many different variables on which to benchmark them. We actually built this thing called WeatherBench 2, which you can go to and check out and explore the kind of performance of these different models. But the big takeaway is that for many of these AI models, they are mostly blue. So in other words, they're mostly performing relatively better than the numerical models at predicting these individual variables. And in fact, the 4 that I've highlighted with this red arrow are ones that have come from Google Research. And if you didn't like all the charts, here's a way of visualizing the same. So on the bottom is that ground truth data set, the ERA5 kind of reanalysis model of global weather. And on the top is the output from one of our AI forecasting models, in this case, NeuralGCM. And, it's hard to tell, is one better than the other, or how close is one to the other? But I think a couple of things. First of all, you can sort of qualitatively see that they're, that the AI model is predicting the same kinds of spatial and temporal trends that you get from the real weather. But I think one of the things that most heartened us when we looked at charts like this and some of the kind of quantitative evaluations based on it was not just that we're kind of matching most of the pixels most of the time, but I think one of the critiques that meteorologists would have rightly given of attempts to forecast the weather with AI was that the AI models are just sort of pattern matching, right? They're just saying, well, I've seen this before, so now I can predict it again when I see the same set of inputs. And then that wouldn't be able to predict new and unseen phenomena. And so one kind of piece of evidence that gave us clue to maybe dispute that, if you just see right now, this little blob that just formed off the coast of Japan and then moved off into the ocean, that's the formation of a tropical cyclone. And there was never a tropical cyclone like that before, right? This is obviously, there's never been any exact replication of the weather patterns as there was before, but this particular kind of phenomena is one that you'd, first of all, quite like to be able to forecast well. And second of all, is kind of representative of that chaos in action. And indeed, we do see that the models are able to kind of reproduce these unseen events by kind of having those input-output pattern matching. And so here's another kind of way that we've tried to quantify that. This is now, again, from the NeuralGCM model, where it's not trying to predict any individual cyclone, but rather the sort of distribution of cyclones over the course of a year. And so in this retrospective analysis, we're able to see that, compared to the ground truth, we're getting the same sort of magnitude and distribution of cyclones over the course of a year. Something that, again, this is a long time for a weather forecast to work over. You might expect 10 days to 14 days at best. But being able to kind of get that distribution of cyclones over the course of a year is something that was quite impressive from this model when we first saw it. And again, we're actually seeing this work in action. So this was a headline from the New York Times a few months ago, showing the output of one of our AI models, in this case, GraphCast, predicting the track of Hurricane Beryl 5 days before it made landfall. And at that time, the kind of state-of-the-art models from the European and American meteorological offices, so ECMWF and NOAA, were predicting that the hurricane would kind of stay south and aim towards Mexico, whereas the GraphCast model estimated that it would head north and make landfall in Texas. And sure enough, 5 days later, that's what happened. Now, this is not, this is definitely a cherry-picked example, but what I liked about it was that, well, first of all, that the New York Times cherry-picked it, not me. But in particular, the headline that they put on the article, which is to say that AI is giving weather forecasters a new edge. This is not to say that AI is better than the other forecasts. In fact, right now AI is heavily dependent on those numerical models for its training data, but that used as an additional tool in the forecaster's arsenal, we might now be able to add extra skill to these forecast models. This is, as many of you probably know, the way that a hurricane forecast works today is within any forecast works today, every forecast is wrong, but some of them tell you something. And so often the case, particularly for these extreme events, what forecasters will do is run a model many times, tens or even hundreds of times, to produce an ensemble of forecasts, and then use the distribution of that ensemble to quantify the uncertainty in where an extreme event might happen. And so in this case, we're just, first of all, I think the AI forecasts add a new source of kind of uncorrelated signal into that ensemble. And second of all, as I showed earlier on, it's much easier to run them much more often. So now we can run ensembles of thousands of members and kind of get tighter error bars on the prediction of those unique and obviously very important events. Okay, so that's kind of it for the sciencey part. I talked about nowcasting with MetNet, and then medium range forecasting with GraphCast, GenCast, and NeuralGCM, as well as kind of some of the longer range kind of climatic forecasting, which is still, I think, a very much active research area. Is how far into the future can we push these models and still retain some skill? but with those kind of hurricane examples over the course of that year, that at least there are kind of statistical forecasts to be made, even if we can't necessarily predict exactly when a hurricane is going to hit, a year from now. Getting distributions on the likelihood of hurricanes and how many hurricanes might arrive is something that I think might be within scope of the kind of next research horizon. But before I end, I want to just talk a little bit about how we're putting these weather models into action. I talked about how we're using them to provide information to Google users, and how we're helping Met agencies put them into their own modeling efforts so they can provide them to all weather users. But I sort of said one of the motivations at the start is that weather is just, or climate is just weather over the long term, and that the way that we're experiencing climate change is through the weather. And so one example of that is in the increased prevalence of floods, both coastal and riverine floods. And so another area that we've been working on at Google Research is around flood forecasting, trying to develop models that can forecast riverine floods, and then use those to both help alert users as well as help response agencies. And so we recently published a paper in Nature about our flood forecasting model, and showed that compared to the kind of operational state of the art, the GLOFAST model from the ECWF, that we can provide the same accuracy that they could offer over with kind of a 1-day forecast that we can now offer with a 5-day lead time. And so this is a model that incorporates a number of AI methods, as well as that weather information. So by obviously a big determinant in whether there's going to be a flood is how much rainfall came into the river basin upstream, and that will kind of then be what causes the river to flood. So better weather can help us make better flood forecasts. And again, this does matter to users. We broadcast flood forecast alerts to users on Google Maps and Google Search. They can be kind of made aware when there's likely to be a flood in their region coming from this model. We also release this data for free in the open on the Google Flood Hub, where you can go and look and or download the flood forecast information, and many of our kind of partners and government agencies do that. And in particular, one agency that we work with, which I'm quite proud of, by the name of Give Directly, they are an international aid agency that donates cash advances, cash transfers to people before disasters hit. And they found in their work that $1 before a crisis event is worth up to $10 afterwards. So if you know that a flood is coming, you can stockpile food, you can kind of put sandbags to protect your house, rather than dealing with the crisis and trying to keep yourself alive and recover from the destruction after a crisis. And so by using our flood forecast, Give Directly has donated this year more than $5 million to thousands of families in Bangladesh and Nigeria, who were alerting that this region is going to be hit by a flood, and they were able to proactively give those cash advances and help them prepare before the disaster strikes. Okay, last one. I would normally ask, does anyone know what this is? But since we're not doing questions just yet, I will tell you that this is an aeroplane contrail. What you might not know, though, are that contrails are responsible for up to 1/3 of the warming effect of the aviation industry. So aviation is about 1% of global warming. Most of that comes from the CO2 emissions from burning the fuel, obviously. But these contrail clouds, which are basically a special type of cirrus cloud, when they form in the wrong place at the wrong time, they basically have an extra effect of trapping heat inside the atmosphere. So kind of a blanket on the Earth. That is, this paper on the bottom left asserts is responsible for up to 1/3 of the warming impact of the ocean. Now, the really nice thing about this is it's going to take us a while before we can go all electric on airplanes. But mitigating contrails might be a much quicker and easier way of reducing the warming effect of aviation. But so how can we do that? Well, this is a map. We built a machine learning classifier to detect contrails in satellite images. Those same geostationary satellite images that I showed earlier on that we use for weather forecasting. We also used a classifier. We first of all labeled 100,000 contrails, and then we built a classifier to detect them. And what you'll notice probably from this image is that they are not uniformly distributed across the US in this case. They're not even uniformly distributed across the flight paths in the US. But you can clearly see that contrails are a weather phenomenon. So they form in a particular part of the atmosphere where the humidity and pressure conditions are such that the crystal, the carbon crystals that come out of the back of the exhaust cause the moisture to collect around those crystals and cause the formation of the cloud. And so if you could forecast the weather conditions at an atmosphere where the contrails are likely to form, then you could recommend flight routes that might avoid them. And so that's exactly what we did. We built a service and worked with this a couple of pilots in American Airlines, where they had their kind of default flight plan, as shown in gray on this chart. And then our model had predicted that based on our contrail detections in the past and our weather forecasts for the future, that it would be likely that there would be a contrail formation up at like 36,000 feet. And so instead, if they fly a little bit lower, they could go underneath that region and hopefully avoid the formation of the contrail and then rise up higher for the end of the flight. And so we did an experiment where they flew, I think, about almost 100 flights and looked at the formation of contrails when they followed our contrail forecast recommendation versus when they didn't, the kind of control. And sure enough, we saw a 54% reduction in contrails with only a 2% increase in fuel costs for the planes that moved. Now, most of the planes were not going to go through a contrail region, so didn't have to move at all, and so no adjustment to the flight plan was necessary. And so for an estimated 0.3% additional fuel cost across the entire fleet, we believe that they could reduce half or more of the contrail formation. So we're now working to extend this pilot. This was just, again, with a handful of flights and a few pilots. We're now looking to extend this into the flight planning systems of more airplanes in the US and here in Europe. Okay, so I'm going to close now and say that, over the last couple of years, I think we've been all astonished by the progress of large models like Gemini and GPT and these other ones in kind of modeling and making sense of all of the world's online information. So text and audio and images and video, and then all the weird and wonderful and amazing applications that's enabled, whether it's like summarizing all of your documents or helping you write code for your next experiment or making new kind of weird and wonderful types of media. This ability to kind of take in all this data and model all these different applications has been quite astonishing. But for me, I think the most inspiring puzzle is to take in not data about the online world, but about the real world. So from the world's weather and climate to maps of the Earth and how people move across it, to photographs of the Earth taken from up in space to all the way down at street level, and use these as pieces of, I think, the most inspiring puzzle of trying to make a model of our planet. And then hopefully use that to solve some of the many, important, exciting, and even existential questions facing us. So with that, I'll say thank you very much, and I'd love to take any questions.
That was fantastic. Thank you very much, Luke. I might, now it's always hard to get a round of applause going when you're on Zoom. I might invite everyone to unmute so we can show our appreciation to Luke for his talk. So I think we're getting unmutes now. So you have a very scattered round of applause now. Thanks, Luke. Very good.
I appreciate it. You're very kind.
Excellent. That was really fantastic. Thanks very much. It's always fascinating, and it's always talked about. I mean, almost every day I'm in UCD. Almost every day we talk about AI and how quickly it's changing and how quickly it's changed. And it must be a very interesting area to work in because it is so dynamic. I might start off with a couple of questions. For everyone else who's here, please feel free to think your question and then jump in after maybe I've had a chance to ask one or two. You can either type it in the text, raise your hand, or just speak when I've finished my questions. So Luke, I guess one of the first ones that I'm interested in, because I plan on using AI in my own research for seasonal forecasting, one of the things that's challenging me is just which approach to take. I mean, there's so many different approaches in AI, and as your really interesting kind of plot that just covered the last few years has shown, it's developing amazingly quickly. So as somebody who's actually involved in developing AI, how do you pick which road to run down?
Yes, I don't have a great answer to that question because I think our approach has been to not pick. I mean, like I said, we published, just as I described there, 3 or 4 different models. Many of these come from different teams within Google who, many of them started many years ago with, some expectation that their method would work or this data set was going to be the key. And as with all research, we hit some dead ends and some of them had some changes and turns, took longer to bear fruit than others. And as a result, we've kind of contributed to part of that kind of Cambrian explosion of all these different methods and approaches. So I suppose having good data and having a good target and then being flexible with the methodology is always a nice approach. Standing on the shoulders of others, like being able to take code that's been open sourced or, model papers that have been published and kind of building on there, like gives you some ability to do that faster. But there's also, something to be said for, picking your one and just, drilling on it until you get it, until you banging on it until you get there, right? I mean, obviously you have to know when to stop, but I think there's, I think in almost all those cases, somebody said, this won't work, this is a dumb idea, you shouldn't do this. And somebody said, I'm going to do it anyway. And
Yeah.
I haven't told you about all the ones that didn't work, but there are a good few of them too. Yeah.
Of course, yeah. That's reassuring to hear. I mean, it's like everybody else's research. Some of it works, some of it doesn't.
Yeah.
I liked the comment earlier, that even if, a few years ago, you may have been tempted to say AI doesn't really have anything to offer, when it comes up against the hard science of, nonlinear partial differential equations. And I mean, I absolutely would have thought that and would have openly said that. And boy, have I been humbled. I mean, it really is very exciting. I think, one of the interesting ways I guess I think about it and I talk about it a little bit is like the laws of physics that we have that we then converted into the Navier-Stokes equations and the other partial differential equations. They're just our own makey-uppy things from lots and lots of observations. And essentially, AI is creating its own laws of physics internally and applying that to the inputs to get the outputs, which I think helps me anyway on a human level understand how it can do what you highlighted, the fact that it can create a cyclone off Japan when that was not there before. And you're kind of going, well, it's got its own kind of laws of physics. We just don't really know what they are.
Yeah.
And I guess
I take the criticism as well. I mean, like there obviously there's something you said, the proof is in the pudding, and if it works, it works. But there's also something beautiful about having an equation that describes how it works, or at least how we think it works. And Sola, asked the question on the explainability part. I mean, I think this is still an open question as to how do you kind of work back. I mean, you'd love to be able to say this was the butterfly whose wings flapped and caused the cyclone, or I know we can't do that with numerical models either, but to be able to have some of that understanding, and I think this is an open question for all fields of AI, is like, how do you poke under the hood and understand what the model understands, and I think that is something we haven't fully. Obviously, we can create charts of every layer and do funny inspections of different weights and that kind of stuff, but I think there's still a lot of work to be done in that realm.
That's really interesting, because that is, as you said, one of the questions in the chat from Sola is about explainable AI, and that's also an area that I've been tracking. I mean, there is a branch of AI that is explainable AI, where I guess it's more the hybrid between physics and AI, but the nudges that AI make are on physics that we can understand, so we can explain. It's not black box. We can explain where it comes from. And I get the feeling, I'm not sure what you've thought in your conversations with users and maybe industry here, that part of it, let's consider Met Éireann. I mean, their role is to protect the state, the people and the infrastructure of the state. Mm-hmm. So if you run machine learning and you get it wrong, and then suddenly you're pulled up in front of a minister to say, why did you get it wrong? You can't just say, well, it's a black box.
Yeah.
Do you think that may impact how quickly traditional Met agencies will move towards fully AI solutions?
Yeah, I'd say two things on that. First of all, I didn't show this chart earlier, but I kind of kept it in my back pocket in case someone asked. The neural GCM model in particular, which is one of my most recent publications, is one I'm quite excited about, because it does at least attempt to kind of integrate physics and fluid dynamics with the neural network part. So we kind of rebuilt part of the dynamical core in a machine learning friendly kind of code base, such that they can kind of merge together more directly with the kind of pure ML parts of it. And so, this is the first publication that sort of shows that. And so there's still, I think, a lot more experimentation to be done of like, well, now could a physicist, for example, tinker with the dynamical core or change something or explain something based on that, while the neural network part's still doing the neural network thing, and and maybe what the kind of bigger question of like, what is that hybrid AI plus physics future look like? So I think there's maybe certainly more research to be done there, and hopefully more questions to be answered there. To your second point about like, if a hurricane wipes out Ireland and the AI didn't predict it, like, who gets sued? Certainly this is one area where I think, like I said, going back to that New York Times headline, we very much want to see these models, used by and work with the meteorologists whose, mission it is to kind of solve those questions and to be responsible for those forecasts. And so, like, I don't think Google is going to be sending out a bunch of, text messages to everyone on search saying like, hey, evacuate your house because we think a hurricane's coming. Like, I know firsthand that we will not be doing that. We would very much like to have meteorologists, put their seal of approval, or find the way that our models integrate with those numerical models and become part of that operational system. Because if it is giving signal, if it is offering scale, we want to be able to take advantage of that. So I think that, again, we're just starting that dialogue now. I'd be, again, very happy to talk to more folks in Met Éireann about how we could do that here in Ireland. We've kind of have early conversations going with ECWF and with NOAA on that topic, but I think it's definitely going to be a partnership.
Yeah, and it's really exciting, for us kind of meteorological enthusiasts to see how closely the ECMWF and the tech companies are working together here. I think that's a really positive and exciting part of
They
this.
are co-authors on that paper that I just mentioned, a bunch of folks.
Yeah, yeah, and I know Peter Lynch, who I think is one of the attendees here this evening. He'd be delighted that you highlighted the neural GCM thing there, because I think that's one of the areas that he thinks is quite an exciting way of blending AI with physics for models that we can use. There's two linked questions here in the chat. That was also something that that I was wondering, and I guess this comes to the overall computational cost. And I may maybe briefly check my understanding here. So, I mean, the AI is trained on Euro 5, obviously Euro 5, massive computational cost to generate decades. I think there's 84 years of reanalysis every 3 hours covering the entire planet. So that's a big computational cost. Then you have to train your model. As far as I understand, that's a very heavy computational cost. At the end of all that, then you run your model, which is orders of magnitude lower in terms of computational cost. But when you take all the Euro 5 reanalysis and the training, can we say that overall AI is cheaper than running IFS, or where do we go on that argument?
I haven't seen the spreadsheet to do that specific analysis and this kind of apples to apples comparison. Yeah, I think your overall summary of the orders of magnitude of each one is probably bang on. I think the training, the details will be in the paper, but we're on the order of days and weeks on not insignificant number of like cloud GPUs or TPUs, but like not crazy amounts. So like training is, I would say, within the grasp of a Met agency, and certainly one who wants to dedicate a bit of AI chops, and then certainly inference is within the grasp of an individual, not quite on a laptop, but maybe on your GPU and your desktop. So I haven't. Yeah, it's a fair point. Like, should we be factoring in the Era 5 computation as well, or they already did that, so that kind of came for free. Certainly, like even just getting access to all that data and reprocessing it and getting it all up in the cloud was many months of work just to kind of wrangle all the data, let alone kind of grind on it. So I mean, this is a big data problem, and I think, and to be quite honest, I think to get better, it's going to have to get bigger. Right now, this is based, as you kind of pointed out, most of these models are based on that Euro 5 reanalysis. I would love to see them being based on or also incorporating observations. But we haven't kind of figured out that data is much messier and harder to get and has to come in real time and has complicated licensing and all the stuff we talked about with the radar, multiply that across all the different observations you might choose to put in there. So this is kind of an aside. There's this science fiction book that I really love and recommend to anyone who's into this kind of stuff by Greg Egan called Permutation City. And it's kind of the thesis of it is basically, we're now in this future where we can simulate brains on computers and like people can live on forever and ever in the digital afterlife. But digital life runs slower because every once in a while the global compute fleet has to go towards running super high resolution weather simulations because we want to be able to control and predict the weather. So like, I mean, this could be one of the ultimate planetary computation problems if you kind of if you wanted to take it there.
Yeah, veering very excitingly into sci-fi there. Let me just come back to some of the other questions here in the chat. So that really interesting. I hadn't actually picked up on that Contrail one. That's really nice use case. There's maybe a related one here. Are you involved in shipping at all?
We haven't done any work. So that Contrail one was a project that we at Google Research wanted to work on anyway. We kind of looked at what are some of the high leverage ways that we could help mitigate climate change. And this was kind of one that stood out. And so then we started grinding on that problem. And then the kind of, I guess, synergy with the weather modeling only kind of came afterwards. We haven't got any internal projects working on shipping, but we are working right now to, I mean, obviously we've published these papers and, made kind of the discoveries available to the world. But like, if you're a shipping company, you're not going to be going through all of the training and technological steps that you've just kind of outlined. So we would like to be able to put these forecasts online for users and let and I think start to think about like the thing that I'm actually kind of most excited about, I think, on the AI forecasting models is not necessarily that they're more accurate or faster, but that they're more fine-tunable, right? So if the thing that you care about is actually wave height in Rotterdam or solar energy production across my set of solar farms in continental Europe, or risk of flooding of all of the buildings in my portfolio, it's obviously a weather adjacent question, but the kind of particular variable that you care requires some specific input from you or data from you, or specific to your problem and use case. And so we think that by putting the models out there, so I think very soon you'll be able to get access to these on cloud, and run it for yourself. And so we've heard interest from shipping people that they would like to be able to do this, and I think this is the way that we can start to kind of enable that.
And that's a really interesting parallel to, as somebody who was born and bred in Ireland, but then I worked in America for a while. And in America, everything's free. I mean, all the National Weather Service, all the data, because it's all paid by tax dollars, it's all free. Whereas in Europe now, I mean, happily, Med Éireann are now in the situation where everything is free. But when I was younger, everything wasn't free. And I mean, I could never understand that, because in America, the idea is give them the data and they'll create a market. Let people figure out what they want to do with it. And I think that's brilliant. And I think what you've said is almost a parallel of that. Put it out there and the end users can figure it.
Yeah.
That kind of maybe segues slightly into some of the other questions here. I might just ask this and then one more before I let you go for the evening.
Yeah.
So the shipping, and there's a question here about geodynamic modeling, which got me wondering, are you only modeling the atmosphere? So are you modeling the ocean, and even crazier, could you model below, the geomagnetic activities and magnetism?
I'd say the reason for the focus on weather, other than obviously weather is awesome, is been number one, the kind of user impact. I mean, everyone cares about it, but like I said at the start. And number two, the availability of that data set. Right? If you ever this is my number one tip. If you ever want a machine learning researcher to work on your problem, give them a nice, clean, easy to access data set, and give them an existing benchmark method that kind of sucks, and they'll be like, oh, I could definitely beat that. And so I would say the same would be true for any of these methods. Like, I don't know the first thing about geodynamo modeling, but if there was an era 5 of geodynamos and a reason to kind of try to beat the current state of the art, I bet that that could be a new research field. Maybe one area that's kind of adjacent that I do think is of interest. The neural GCM model that we talked about earlier, and its kind of potential application in kind of beyond weather horizons, like into subseasonal and even climate distances, we know will, even with the best AI and the most data, will fall because it is only an atmospheric model, as you said. And so we don't have a ocean couple model or an ice cap model or atmospheric chemistry model or any of the kind of things you would want in a real deal climate model. And so if you think about, well, what would the AI climate sim look like? It would obviously have to incorporate those aspects. And so how might you create the data sets and build the models and couple them all together for those things that will be, in the AI paradigm, the way that we have done in the sort of numerical world. So that's, I think, again, an open and interesting research question, one that we have some ideas on, but nothing kind of concrete, I'd say, yet. And I would love, again, if there was the Era 5 or similar of all of those domains, I think it could be quite transformative.
Yeah, that's a really good point, actually. With the Earth system models that we use for climate modeling are, of course, arguably the atmosphere is less important than a lot of the other parts in the Earth system when you're looking at the decadal and longer scales. But at the same time, we spend so much computational power, let's say, going from global climate models to our regional climate models, that I think there is very good potential there. So I'm not sure, straying off into maybe the minutiae here a little bit, but I mean, the CMIP6 GCM data is still not available on Eurocortex, which basically everyone is outraged about at this stage, to the point that some countries in Europe are now going to develop their own data before the Eurocortex CMIP6 has been released. And obviously that cannot happen again. So that makes me wonder if this is, again, a fortunate time for AI potentially to extend into regional climate modeling.
We did a lot of work to get the Era 5 data, not just available for ourselves, but online and available for anyone. So it's on cloud, hosted on cloud. You can download it for whatever the data egress costs are. Again, it's free to access. And that's the link there. There's even kind of code libraries for doing it. But you're completely right that we'd love to be able to do that for the even larger, even heavier weight data sets that come from these climate models. It's an IT challenge much more than a research challenge at this stage.
Yeah, very interesting. Great. I might just close off maybe with this question from Evelyn. Evelyn, you're not online, are you? Could you ask the question yourself? It's just I'm not entirely sure that I get what your point is from the text. I'm not sure. Is Evelyn Murphy still there?
I think what she's getting at is, I hear the immediate point that this brings to mind for me is that, as I showed in some of the charts, so all of these models to do the paper were based on the Era 5 analysis. This is like a nice, like I said, offline data set. It just exists. You got 40 years ready to go. It's no good for an operational model, right? For an operational model, you need like what's happening right now and then what's going to happen next. And Era 5 doesn't capture that, right? So the kind of transition from the research version to operational versions that were going on, and why I want to be able to kind of make shipping forecasts available on cloud, involves sort of retraining or at least fine tuning on the operational forecast model outputs, so like the HRES or whatever else. Just today or like very soon this week, these MWF are going to 49R1, like the newer version of their model. And so, some of the variables will slightly change, and some of the, models that made the model that made those variables will be different. So the kind of distribution of that data will definitely differ from ERA 5, which we know about, and it will even differ from the previous model of these MWF forecast. And so how do you make sure that your model doesn't kind of just grab onto some, esoteric change in the distribution of the data rather than the actual realities of the change in the weather? And so this is like a very, very, very important question, certainly for research, but definitely for kind of trying to use any of these AI models operationally. So, having real-time validation, retraining based on, just all the time, but certainly based on when distributions of the input data have changed. And I think, for want of a better word, keeping an eye on things, like looking at, are your predictions making sense? Do they correlate with the other models that you're also running? Do they correlate with ground truth? Having alerts for all of those things, like this is a big part of kind of going from research into operations and making these things real. So, but that's all new stuff, right? I mean, it's not new in the sense that weather forecast has been doing this, and numerical models also do this, but like certainly in the kind of AI paradigm of that, it's also not new in AI models for other domains, right? The internet also changes. People write about new things and new stories come up, and like we saw those funny things where ChatGPT didn't know about anything that had happened prior to or post 2003 when it first came out, and this kind of stuff. So like having these kind of real-time pipelines and the kind of validations of them is something that we at least understand is a challenge for kind of using AI in any kind of practice, and it's certainly one that applies to weather as well.
Brilliant. Well, listen, thank you very much, Luke. That was really fascinating talk, and really great Q&A afterwards. I think I personally am delighted that I got to pick your brain every single day.
Yeah, no, it's my pleasure. I really appreciate the opportunity to talk to you all, and glad to be working on this in Ireland where we love the weather so much. And look forward to next time.
Yeah, indeed. Okay, so thanks everyone. Thanks Luke for the talk. Thanks all the rest of you for showing up. We will have an in-person talk next month.